So we now need to explore linear independence and dependence of sets of vectors that contain one or two vectors only. Now, when we're considering a set of vectors with one or two vectors only, we don't need row reduction. It's unnecessary. In these cases, we'll be able to use visual inspection. So let's consider these cases. So case 1, let's consider the case where we have a set with one vector, v sub 1. So a set containing one vector is linearly independent when, or if and only if, vector v sub 1 does not equal the zero vector. So in other words, the vector equation, say x sub 1 times vector v sub 1 equals the zero vector, has only a trivial solution when vector v sub 1 is not equal to the zero vector. So a set containing a single vector is going to be linearly independent every time except if that vector is the zero vector. Now, we can pretty easily check to see why this isn't holding true. So let's note that the zero vector is linearly dependent because infinitely many non-trivial solutions exist, or because the vector equation has infinitely many non-trivial solutions. So the zero vector is linearly dependent because the corresponding vector equation has a non-trivial solution. So let's go ahead and check this. Let's let vector v sub 1 be equal to the zero vector. So then the vector equation will have the following form. We will have our weight or scalar x sub 1 multiplied by the zero vector is equal to the zero vector. So let's see if we can come up with some linear dependence relationships. So remember, to come up with your linear dependence relationship, we simply need to choose a value for x sub 1, our free variable, if you will. So what about if we let x sub 1 be 1? Well, 1 times the zero vector equals the zero vector. So that satisfies the vector equation. What about if we let x sub 1 be equal to 1,321? Well, 1,321 multiplied by the zero vector still equals the zero vector. So this is still satisfying that vector equation. So what this is showing us is that the vector equation has a non-trivial solution. There are infinitely many solutions that satisfy the vector equation. There exist infinitely many solutions that satisfy this vector equation. So therefore, the zero vector is linearly dependent by definition. So this really drives home to us that a set containing a single vector is linearly independent as long as that vector does not equal the zero vector. Because in this case, there's only going to be one weight that satisfies the vector equation. So if we suppose that vector v sub 1 is any vector in Rn except the zero vector, there's only one scalar that will satisfy this vector equation. 0. So 0 times this vector v sub 1, as long as it's not the zero vector, is the only scalar that satisfies this equation. Now, what about the cases where we have two vectors in the set? So we're now ready to consider our second case, a set containing two vectors. So we say that a set containing two vectors, say vector v sub 1 and vector v sub 2, this set is linearly dependent if we can write vector v sub 1 as being equal to a scalar c times vector v sub 2. This again is such that c is some scalar value. So in other words, these two vectors are linearly dependent if they are scalar multiples. So a set containing two vectors is linearly dependent if the two vectors are scalar multiples of each other. Now, geometrically, what this is telling us is that these two vectors lie on the same line. So vector v sub 1 and vector v sub 2 lie on the same line. Now, a set containing two vectors is linearly independent if the vectors are not scalar multiples of each other. So if vector v sub 1 does not equal a scalar multiple of vector v sub 2, then the vectors in the set are linearly independent. So again, the set containing these two vectors is linearly dependent if the vectors are scalar multiples of each other. Versus, we have that this set containing two vectors is linearly independent if those two vectors are not scalar multiples of each other. So let's consider a quick and cute illustration. Let's suppose that vector v is defined as the vector 2, 2. And let's let vector u be defined as the vector with components negative 1, negative 1. And we'll throw in a third one here. Let's let vector w be the vector with the components negative 2, 3. And so what I'd like to do here is let's compare two vectors at a time. Let's think about what's going on with vector v and vector u, or the set containing vector v and vector u. And then we'll go ahead and let's compare vector v with vector w. So here we go, case 1. Let's plot these vectors. We have vector v at the point 2, 2. So here is our beautiful vector v. And then we have vector u at pointing to the point negative 1, negative 1. Now, even though these two vectors are pointing in the opposite direction, they exist on the same line. So we can even take this one step further as math enthusiasts and say, well, since vector v is equal to minus 2 times vector u, they're scalar multiples. Woohoo! So we can say that, therefore, the set containing the vectors v and vector u is linearly dependent. So because these two vectors are scalar multiples, or because they lie on the same line, the vectors are linearly dependent by definition. So now let's think about the case where we have the set containing vector v and vector w. So we already have vector v graphed, beautiful. And now we have vector w at pointing to the point negative 2, 3, so right about there. So here is our vector w. So just by visual inspection, we can see that these two vectors certainly do not lie on the same line. So since vector v does not equal a scalar multiple of vector w, and again, this is where c is some scalar value, we can say that, therefore, this set is linearly independent. So because these two vectors are not scalar multiples, they are linearly independent, or they form a linearly independent set. Now, just for fun, because math is fun, what about the set containing vector v, u, and w? Well, this set contains 1, 2, 3 vectors, So we cannot use visual inspection here. We would still need to go ahead and check this. But this actually leads us to our next theorem and shortcut. So get excited.